AP Calculus AB, Unit 6, Day 13, Assignment 13, Office Hours. These answers you should have checked already. These are just the answers. I will show them very quickly. You can pause the video if you need to. But that's just in case you haven't seen them yet. Pause it if you need to. Okay. Okay. So the first question says if B is on fx and BA is on the inverse, then the slope of fx at x equals a is equal to the reciprocal of the slope of the inverse at x equals b. That's the basic idea. If f is increasing and concave up for all x, then the inverse is what? Well, I would draw a sketch and say, okay, well, it's increasing and concave up. So then you flip it across y equals x, and it's going to be increasing and concave down. Increasing and concave down. Little sketch always helps. So now for some inverses. So find the slope of the inverse at x equals 4. So what I would do is I'd say, well, x equals 4 is on the inverse, which means that y equals 4 is on the original function, which means we could set the y value of that function to 4 to figure out what the x value should be, plus or minus 2. Now it's going to be the positive 2. So this is on the original function. So what I can do now is take advantage of, let's just take the derivative of the original function, which is super easy. Let's plug the corresponding x value in. So x equals 4 on the inverse, but that corresponds to x equals 2 on the original function. And then let's flip it to find the derivative of the inverse at 4. So 1/4. That's the new school approach. I'm not going to show you the old school approach. If you look at my solutions, you can see the work. It's always harder. It's always more work, and sometimes impossible. We did number 4 in class together, or in my last lesson. There's the work if you need it. Number 5. So x equals 12 is on the inverse function, which means that y equals 12 is on the original function, which means if I plug 12 in for y on the original function, I can find the x on the original function. Plus or minus, positive. So we're going to go with the positive. That's on the original function. So now I can take the derivative of the original function, which is pretty clean, and plug 3 into it. And then flip it to get the inverse derivative at 12. That's the quick way, and in some cases the only way. Number 6, find the slope of that. So x equals 28 is on the inverse function, which means that y equals 28 is on the original function, which means if we plug 28 in for y in the original function, we should be able to solve for the x on the original function. But we want the positive one, otherwise it wouldn't be a function. So this one is on the original graph. So I'm going to find the derivative of the original graph and plug in the correct x value that corresponds to the one we're interested in on the inverse. And then I can just simply say the derivative of the inverse at x equals 28 is the derivative of the original function at 5 flipped upside down. Not negative reciprocal, just reciprocal. Number 7, x equals 20 is on the inverse graph. Therefore, y equals 20 is on the original graph. So we plug 20 in. I'm going to solve it. It's quadratic. I personally like factoring over quadratic formulas and stuff like that and completing square. So that's going to be x minus 4x plus 5. So we get x equals 4 and negative 5, but we're going with the positives this time. And that's on the original function at the point. That's the point we're interested in that corresponds to x equals 20 in the inverse. So I'm going to just define the derivative of the original. And I'm going to plug 4 into it. And then I'm going to use that to find the derivative of the inverse at 20 by simply flipping it upside down. That's how you do it. Okay, now number 8, they give you the function. They say the derivative of the inverse is what? Now, that means the derivative formula. Now, there's no shortcut for this. You can't just take that derivative and flip it upside down. I bet one of these answers might be that. So someone might think, oh, okay, well, let's take the derivative of this. And then just flip it upside down to get the inverse derivative. That doesn't work. So this is not the right answer. And I guess luckily they didn't put it on there. I mean, they put something kind of close. Well, something close. I think that's slightly off. But anyways, that would not be the approach. So this one we have to just do it the old school approach because we want to find the actual equation, not just a single point. So we need to take the original function, and swap the x's and y's. Right? We could flip both sides upside down, take the cube root. So y equals the 1 over the cube root of x. That's the inverse function, and so now we're going to find its derivative formula. I'd go back to, I'd say, oh, this is the same thing as x to the negative 1/3. So that's going to be negative 1/3 x to the negative 4/3, which is negative 1 over 3 x to the 4/3. That, this, let's see, which one of these negative, looks like a B is the correct answer. Even though I picked something else, it might work. Okay, what did I do wrong? That's what I did wrong. It should be a 1/3 right here, right? So this should be a 1/3, which means that we should cube both sides. So that's y equals 1 over x cubed. Which would be x to the negative 3. So that would be negative x to the negative 4th, or negative 3 over x to the 4th. That's what we're looking for. So the answer is negative 3x to the negative 4th e. I made a little mistake there. All right. So we had to do that one old school. 9. The derivative of the inverse of x equals 8. So x equals 8 is on the inverse function, which means y equals 8 is on the original function. which means if we plug it in, we can find the x value on the original function. Now, this doesn't have any domain restrictions, but all the answers are positive, so I'm assuming we're going positive. So the derivative of the original function is 2x plus 2. And so if we plug 2 into that, we get 6. So the derivative of the inverse function at x equals 8 that corresponds to that point is just going to be that slope flipped upside down. So that's how you do it. It's the best way to do it. Got a couple more of that. So we're trying to find the derivative of the inverse x equals 8. So x equals 8 is on the inverse, which means that y equals 8 is on the original graph. And we can plug that in. And then we can factor it. And this time it's clear we want the positive. So then I'm going to take the derivative of the original graph and I'm going to plug 2 into it. And so then the inverse graph at x equals 8 derivative is that flipped upside down, 1/6. Number 11, they give you a function f of 2, so that's the x and the y on the original function. And they give you the derivative at x equals 2. So the inverse function, if x is 2 and y is 7 on the original graph, then that means that corresponds to 7 comma 2 on the inverse graph. And right here they're saying, well, what do you get if you take inverse of 7? You get 2. They flip places, right? If you have the slope at this x equals 2, then the slope at 7 right here on the inverse is going to be that flipped upside down. It's as quick as that. I just gave you the value. So this time you had to use the new school approach because I didn't even give you a function. I gave you limited information, limited numbers. Okay, the rest of the problems are just some more review of derivatives of logs and exponentials. So I'm trying to find dy dx, combine like terms, reduce no negative exponents for final answers. We got to do a little product rule here. X squared times derivative of that's going to be 1 over sine times derivative of what's inside, chain rule, cosine, plus natural log of sine x times derivative of x squared is 2x. And clean it up. This is going to be x squared cotangent x plus 2x natural log of sine x. You want to put that 2x in front of the natural log. That's it. Done. 13, y prime, or dy dx. All right. Exponentials are their own derivatives. Simple as that. Then, of course, like always, you got to do the chain rule. So the next one is cosine. Leave the inside the same. And then you got one more chain rule inside that, which gives you another 6. So your final answer for dy dx is 6 cosine 6x e to the sine 6x, something like that. There you go. Number 14, you could just tack it straight on. Y prime equals derivative of any log is 1 over what's inside. But if it has a base of an e, then you need extra natural log of the base. And of course, you need to do chain rule times derivative of what's inside, which is involved product, so you better put parentheses. X squared times derivative of sine is cosine plus sine x times derivative of x squared is 2x. And then you could clean it up. X squared cosine x plus 2x sine x all over x squared sine x natural log of 2. But you could also use log rules to make this easier, right? So you could use log rules. Log rules, you split it up. It's called log, so this could be log base 2 of x squared plus log base 2 of sine x. You move the 2 out in front, and then we take the derivative of that. And avoids the product rule, avoids some of the chain rule stuff. So that would be 2 times 1 over x natural log of the base plus 1 over sine x natural log of the base. That's it. Oh, wait. Times derivative what's inside. Cosine x. That's it. So 2 over x natural log of 2 plus cosine of x over sine x natural log of 2. Now, if you wanted, you could combine these into a single fraction and probably give you that answer. So if you did that, just as a comparison, 2 sine x natural log of 2 plus x natural log of 2 cosine x all over x. Well, we both have natural log of 2, so we don't need to multiply an extra natural log of 2. Both have natural log of 2. This one uses sine x, this one uses the x. And if you look up here, well, this one we could have simplified. We could have divided an x out of everything on the top, right? That's why mine wasn't working exactly the same. All right, so you have x cosine x, 2 sine x over x natural log sine x. Same thing. Same thing. Different options. Okay, number 15, y prime equals 1 over what's inside. Derivative of what's inside is exponential, so it's its own derivative, but it needs an extra, natural log of the base, which is 4. Don't forget that. And then times the derivative of what's inside. Derivative tangent is secant squared. So there it is. We can simplify. These guys actually cancel each other out, and you get natural log of 4 secant squared x for your final answer. Or you could do log rules first a little bit and rewrite this, put the tangent x out front, right? And then derivative of this, don't need product rule. Natural log of 4 is just a number. Natural log of 4 times derivative tangent is secant squared. Boom, same answer. Bit less complicated. No chain rule. All right, number 16. 2 ways to do this. You could tag it straight on and do the whole quotient rule thing, low d high minus high d low all over low squared. And then you just got to clean it up. Lots of fun algebra. So you got to FOIL it. So you get 2e to the 4x minus 2e to the 0 minus 2e to the 0 plus 2e to the negative 4x minus 2e to the 4x plus 2e to the 0 plus 2e to the 0 plus 2e to the negative 4x. And you got to distribute that all over e to the 2x minus e to the negative 2x squared. You can multiply that out too if you want. These are going to be 1s. So you have a 2e to the 4x minus 2e to the 4x. You have a 2e to the negative 4x minus a 2e to the negative 4x. You have negative 4 minus 4 gives you negative 8. So, I mean, we could write the answer like this. We could simplify the denominator. It'd be e to the 4x minus e to the 0 minus e to the 0 plus e to the negative 4x. These are going to be 1s. But we don't really like negative exponents. So this would be 1 over e to the 4x. So to get rid of the fractions and fractions, you can multiply by e to the 4x, top and bottom. And you get negative 8 e to the 4x over e to the 8x minus 2e to the 4x plus 1. But an idea that might be nice is at the very beginning, take care of those negative exponents right away. And then you don't have to do it later. And I think it also makes the work a lot cleaner. So multiply the top and bottom by the least common denominator. You get e to the 4x plus 1 over e to the 4x minus 1. And take the derivative of this instead, which I think would be a lot easier. And then the negative exponents are already taken care of at the end. So different ways to do it. Okay, number 17. I mean, I'd use log rules here, break this up. And I bring 3 out in front and 2 out in front, and I take the derivative implicitly. So this would be 2 times 1 over x plus 3 times 1 over y dy dx equals e to the sine 2y times cosine 2y times 2 dy dx. So that's the derivative. Now you got to get the dy dx by itself. So it's a bit of a mess. But we could say, all right, dy dx, we have a 3 over y. Move this over this side, minus 2e to the sine 2y cosine 2y. And move this guy over the other side. And then divide both sides by this. I don't want fractions and fractions, so you have to multiply top and bottom by the same thing by an xy, and that should take care of your problems. Make it a nicer, cleaner fraction. So it's going to be negative 2y over 3x minus 2xy e to the sine 2y cosine 2y. Yeah, that's probably the better way to do it. I think I have the work for if you just tackle it straight on without log rules. There's no way you're doing it explicitly. There's no way you're going to get y by itself. There you go. Some good practice.